Last week, we climbed a very steep mountain. If I remember correctly, it was like 6 or 7 hills that we climbed, yes? But I think I had a pretty good feeling that by the end of it, I think you understood what we were doing, yes? Okay, so today what I'm going to do is I'm going to start not where I ended. I'm going to start a little bit before so we get some impetus and we can climb the rest of those mountains. We're going to get to the peak of that mountain today. Then we're going to look around, look at the landscape, and that's the end of it. What I will do next week is something entirely new. So today we'll put an end to all of that. And I remind you that what we did last week was I started with this 33-cent game. We're gonna get a lot of mileage out of that. And we looked at that from different perspectives. The perspective I'm most interested in today is the mathematical perspective. Today, I will actually prove a theorem for you. It's the fundamental theorem of asset pricing. So let it be known, I'm gonna prove a theorem. Yeah, it's pretty close to a proof. And for that, we developed some formalism. I want to review the formalism we went through last week, knowing that now you understand what's behind this formalism. This formalism is not just an invention. It is what we need to develop so we understand securities markets. Without it, understanding securities is going to be quite difficult. And you will, in complex situations where the 33-cent game gets incredibly complicated, you will not understand what's going on. But with this perspective, we will understand what's going on. So I remind you that here, what we were doing is I created a probability space on which things happen. And we call them events, and we considered prices under each of those events. We considered securities. I said it's a finite number of securities, but some of you were very curious, like you, about what happens if there's an infinite number of securities. Today, your answers will be answered. Sorry, your questions will be answered. Okay, everything I will do today, I will do in finite dimensions. If you are afraid of infinity, you're fine. But I want to do them in such a way that for those of you who are interested in the infinity, you're going to say, oh, yeah, that's how it's done. Okay, I could do that. Okay, so I won't do it here, but you can go home and you can do it yourselves. Actually, that would be a very good challenge. And, and for that, we created the payoff matrix. The payoff matrix will tell us the value of each security under each possible scenario in the future. And it's going to be a matrix, perhaps not a square matrix. It'll be a square matrix if we have as many scenarios or as many events as we have securities. Our 33-cent game was one of those cases, but then we also saw examples last week in which we had more scenarios than securities. And you can easily imagine situations where you have more securities than events. To simplify our terminology, we're going to assume we're going to say S naught is our bond, and which means that we know it's the only security that will have predictive values in the future. And with the payoff, we defined or we introduced the cost vector. The cost vector is one that will give us the value of each security today. We saw the relevance of that. In the 33-cent game, we played with a stock whose value today was 1. And its future value tomorrow was either 2 or a half. So the 2 and a half are part of the payoff matrix. The value today, 1 is part of the cost vector. The bond was easy, always 1 tomorrow. Today, well, depends on interest rates. So the cost would represent interest rates, and the payoff matrix for the bond is trivial, is 1, 1. That's why we call it S naught, because then we somehow know that every time we have a universe of securities, the first one is the trivial one. There was always going to be a trivial one, and that's the bond. And this is what got us started into the 33-cent game. Now, the setup is much more general and could help us understand many things. In fact, today I will prove that the yield curve exists by following exactly the same formalism that we developed for the 33-cent game. So today we're going to see the relationship between the 33-cent game and your assignment number 1. It may seem there is none, actually it's the same thing. And then we'll have that big understanding. That is the mountain we're climbing today. If you think that the 33-cent game and your assignment number 1 are unrelated, no, they're exactly the same thing. Okay. So we will have financial instruments. We always have that. In your case, assignment number 1, you have bonds, coupon-bearing bonds. And what you're essentially doing is finding the price of 0 coupon bonds. That's a way to think of assignment number 1. In our 33-cent game, we had a bond and a stock, and then we priced an option. It's always the same. You are given some securities to find the price of others. That's the perspective we're adopting today. And that's where your assignment number 1 and the 33-cent game meet. And for that, we're going to develop a theory for which we will assume a number of events and a number of securities. Again, finite, but today it will become very clear what will be required if we want to go to infinite. Matrix and a vector. And linear algebra is going to be our best guide through all of this because it's not a surprise. Linear algebra will dictate how all of these prices are consistent with each other. We already saw that last week when after the initial surprise, I showed you how to create the replicating portfolio, and then we showed us the solution of a very simple system of equations, 2 by 2. So we're taking that into an abstract context today. That's all we're doing. We also considered the situation of markets where things don't quite work. We call them incomplete. And that's going to become very clear also today. All right. I review the example for you. If I have a stock that is a value at $1 and tomorrow things could happen, then we know the answer is 33 cents for the price of the option, which is here denoted by the number V. But with this situation, we have a payoff matrix given by column 1, 1, column 2, a half, representing the future values of my 2 securities. We want to generalize this to, we have the cost vector that tells us the price of securities today, 1 for the stock, 1 for the bond. So here we see that rates are 0. And then we saw that the span of this is all of R2. So we can price anything. We can play any game. We can price it. We saw that. And there's a replicating portfolio. Replicating portfolio were important for us because they told us, if you're a bank, for example, selling the options to someone, tell you how to hedge it, meaning how you can sell that and not lose money. And then I remind you, we're working for free for about 3 more weeks. But that's going to give us a very good compass how to make money, because then this is the price, then you add a fee to that, and the fee is yours for sure. No speculation. We also saw a situation where a stock value, say 1 today, could have 3 values tomorrow. If the only thing I have is a bond, then my payoff matrix is like this: 1, 1, 1 for the bond, and then 2, 1.5 for the stock in this particular situation. And now we see trouble because we see that the span of this is not all of R3, which is all of my possible payoffs, and then there will be securities we cannot price. But the setup is the same. I also have a cost vector, which in this case tells me what the interest rates are. This is an example of a payoff that cannot be priced in this particular situation because this payoff is not in the linear span of the payoff matrix. We saw that also last week. Yes? Okay. All of this is the review of everything we saw last week. Okay? So we get impetus and then we can climb this hill today without much effort. But if someone gives you the price of the option, someone out there, a liquidity provider says, you know what, I'm willing to sell the option for a third. So in that case, your market in this particular situation is complete. As soon as you know the price, as soon as the cost vector is expanded with another entry, with a new payoff that helps you span all of R3, then Your payoff matrix is square, non is invertible, and therefore we know in this case that we will be able to price anything, and the cost factor will be this. That will be the reality for this. And this is a situation that if you have a million securities with a million scenarios, they say, well, that's okay. You can put all of this into Python, and calculate the payoff matrix, and you can do everything that we did last week. The 33-cent game will work anywhere. Yes? All clear, right? But we need to understand what it is that we're doing. We need to understand the market that's ahead of us, because otherwise we may be confused as to what to price and what not to price. In this particular example, we can see how I can price another stock option that will give me money if the stock drops, nothing otherwise. By the way, this is called a put option. And we can price this from first principles. We know with the payoff matrix we can price anything. So we will solve a certain system of equations, and off you go, you price this. Okay. And all because the span of the payoff matrix is all over 3. So everything can be priced. We saw that last week. And from here, we saw a general method of pricing and replicating. Given securities, payoffs, and cost vectors, a security with a payoff vector given by anything can be solved. You can always find a portfolio, a vector in this case, such that the replicating portfolio times the payoff matrix gives you that. If you notice, this linear expression I have here is exactly the linear expression we needed for the replicating portfolio, right? Do the calculation, do the multiplication of the replicating portfolio, which is a vector of weights, times the payoff matrix. Each weight multiplies the column. The column was the instrument, right? And it's the sum. So that is the payoff of the replicating portfolio. And I'm saying the replicating portfolio equals the payoff given. All right? Yes?
Back to like the previous 2 slides, why was the third instrument priced at 100?
You're asking me again?
Like, you know the matrix, right? It was incomplete before, but then we got a complete matrix. I
Right.
don't understand where like the 1 is. Isn't the option priced at 1/3?
The payoff, what's the payoff of this security?
$1 and then 0,
100, right?
But then for this next slide, wasn't it 0.2?
Look.
And then for the next one.
You mean here?
Yeah. This is.
What's your question?
This one's 0.2, right? But then.
Yeah, this is a different one. I call this is O2. This is option 2.
Option 2. But then why was like the third column of the matrix the same?
Oh, I don't know the price of this option. Oh, this is very important. This option is introduced, but I don't know the price. I can price it because I know the option price of the previous slide. Yeah, okay. Yes. This is important. Okay, I almost lost you. It's very, very easy to catch up. Yes? Okay, I'll say that again. You?
So let's say if I wanted to price this option, right? I wanted to find X.
Yes.
So I would find sort of the unit combination that gives me 0, 0, 0.
Exactly.
And then sort of add up the numbers.
Exactly. Yes. So this is an option that I have to price. The previous option, 100, I cannot price, but someone gave me the price. And that's why I have a cost vector. Someone said, I'll sell it to you for 1/3. Thank you. My market is complete. Now I can price this one. It could happen that someone says, oh, the price of this is, I don't know, 10 cents. Thank you. Then I can price the other one. I just need one of these 2 options to be priced, and then I can price the other one. This is important. So here I gave you the situation where my market was completed with the price of option 01, the one whose payoff is 100. Yes? And then we see everything can be priced because the span of that is all of R3. Imagine for a second the reverse, that this option you have here, 20 cents. This option, someone sells it for 10 cents, say. But no one is selling the previous option 100 for a third. No one is selling that. They're selling this for 10 cents, right? Then I can price everything. Why? Because my payoff vector is, my payoff matrix is no different. It's 111, 21, half, 0.2. Still spans R3. And if the cost vector, if the cost of this option is known to be 10 cents, then I can price the option 100. You just need to complete the market with one security. That's all. And then you can price all others. This is important. Yes? There's nothing special about 100. I just took that, say, well, if someone prices that at 33 cents, then I can price everything else. If someone prices 20 cents, 0.2, someone prices that, then I can price everything else. Or if someone prices 0.10 payoff, then I can price everything else. I just need a third vector to complete my three-dimensional Euclidean space. Whichever ones they are, we don't care. All good here? Everybody? We need to be together on this, okay? This has to be, we're climbing this together. Yes?
Still don't get why we can price a different option with the original, like, an option that was already priced for us.
Sorry, say that again.
Like, so we have a complete market now, right?
Now we have a complete market, yes.
So then how do we price a different option?
How we price, for example, this option? Okay, so I'm going to give you the formula, but until I give you the formula, you can do this yourself, right? What you will have to do is you have to figure out what is the linear combination of those three column vectors that give you the vector 0.2. Once you have the linear combination, I said, okay, so I have to buy these bonds, buy this number of stocks, and buy this number of options, positive or negative. That's your replicating portfolio. And so if I know the replicating portfolio, what's the price of the replicating portfolio? All three instruments have a price, so the replicating portfolio has a price. So that's the price you charge. By the way, that's how you hedge it with the replicating portfolio. So you just go, wait, have your dinner, and tomorrow your replicating portfolio will match the option. Yes?
So, theoretically speaking, there could be a case where X is negative. Then what would that imply?
X is, what's negative?
So, theoretically speaking, there could be a case where my X is negative.
What is X?
The price of the stock option O2.
Yes. Yes?
What does that imply then?
Okay, so the price of this can never be negative. Okay? Because then you'll have an arbitrage opportunity. So, well, that's the theorem we're seeing today. But forget that, right? Forget that. The price that we get here is going to be the value of a replicating portfolio. The replicating portfolio is obtained by solving a certain system of equations. And the question that the price has to be a positive, I can give you an arbitrage-free argument, which is if the price is negative for this, that means you can buy it for free, and then you will have arbitrage. And then you say, well, how do I know that then you can do this in one way, which is you can do a fairly tough linear algebra assignment, which is proof that the solution to this, okay, that you can, if any one of you is TA in linear algebra, you can do this as an assignment for people doing, and they will sweat and so, how do you do this? Today we're going to see the answer to that, because that's the theorem. Okay, yes?
Just going back to the previous slide when we introduced like the price of 1/3
Yes.
for the new option.
Yes.
If someone came into the market and undercut them, would that mean that all options change?
Okay, yeah, okay,
all
no.
option prices?
So if someone comes to the market and undercuts them, that's an arbitrage opportunity, right? Because you have two people offering a different price for the same thing. Here we're assuming that that's impossible. And like I said, I cannot assume this is impossible forever because things happen. But I need that assumption so we can build this theory. And I need 2 more weeks of that assumption that this doesn't happen. Of course, this happens, especially when we look at investments in about a month or so, month and a half. That's how investments are made. And typically, it's not that someone can make money for free. We will see that even in the case of investment, that's very, very rare. But if that happens, someone undercuts you, we're going to have situations in this classroom where 2 of you will be undercutting each other. It'll happen, okay? It'll happen. It's coming maybe in a month. But if that happens, again, this is not consistent with this theory. For that, we have to into the concept of competition, and then of course arbitrage exists, and this and that. That's coming. But if that happens, then you can assume that the price formation changes once someone gives you a different price for something, and then the old price is obsolete. The market will ignore it. Like you can offer this for a third. If someone offers that for 10 cents, then that's it. Your price is now not part of my theory because no one will go with yours. If anything, they will short sell yours, buy this other one, which means your security, and no one will ever offer that again. We are not adopting that point of view yet. It's very important for you to understand that the reason we are following this arbitrage-free context is so we can have the theory of the unique price. Once we have that, then sure, bring me whatever you want. I already have a theory and I can see how we can make money off it. But for that theory, we're developing today the theorem of the unique price. For that, I need no arbitrage. If I have arbitrage, great, let's all make money and forget about the theorem. But do me a favor, let's do that after we see the theorem, okay? We'll be in a stronger position to understand that. In fact, the theorem will tell us where to find arbitrage. There is one indicator that will flash red, and then we will know there is arbitrage, and then quickly go find it and go make money. That's part of the theorem too. There will be a flashing indicator. Okay? Yes?
So, like, could you explain more about the vertical vectors? Because, like, the P, we know is the payoff matrix.
Yes.
And then the first vector is the bound.
Okay, so let me say something. The payoff matrix, this is a matrix that, matrices have two purposes in life. Two, right? The most important one is to organize information. Every time you do a spreadsheet, you have a matrix, right? Most spreadsheets are matrices. That doesn't mean they have any linear algebra meaning. If I give you the dates, and then I give you how much you eat on that day, that's a matrix. As far as I know, it has no linear algebra component. It's just a way to organize information, right? So we agree on that. Great. So you could say, well, I'm just organizing all of my information in this matrix, where I put in my columns the future possible values of each of my securities. So think of it as a way to organize information. It's nothing but an array on Python. However, in our case, it's much more than that. It also is a matrix from a linear algebra interpretation, as we're about to see. Because this is a matrix that we can invert, we multiply by something, and that will give us prices. So this is a matrix that has not only the property that it organizes information, it's one that will also, as we are about to see, will also be the one that gives us prices. We already saw that before I got the question. I'm going to come back to that. Yes? So you could say, I want to organize information differently. I want to put my instruments in rows and my future values in columns. when you do this in Excel, you get to choose, right? What's your column? And I could do that too. In which case, by the way, I could do that. I could write my matrices with organizing the information differently, right? I could do rows for the instruments and scenarios for the columns. That's fine. And some people do that, which means every formula I will give in this course, you have to take the transpose to match this other book that does it differently.
Yeah, but a follow-up to that is that, like, the second column is the stock price, like the stock
The
price
stock payoff.
payoff.
Yes.
And then the first, it seems like the first and also the third, they are both options. Like the first is bond price.
Okay. So remember the setup. When I do the setup, I say I have securities, and I call them S0, S1, S2, S3. I didn't say they're stocks, they're bonds, they're options. It doesn't matter. They're securities. Securities are what? In our context here, in our definition, a security is something that has a value today, the cost, and future values under all of my scenarios tomorrow. So a bond is a security. Stock is a security. An option is a security. And for this theory, it makes no difference what they are. There could be two stocks. It's kind of weird because you think, well, a stock will have its own behavior. This stock will do one thing, this other stock will do another thing. So how can I have only 3 scenarios with 2 stocks? I would need 4, right? Well, you understand what I'm saying? But in this theory I'm developing, I don't get into that. Yes, sure, if you're modeling 2 stocks, I would expect 4 scenarios. But guess what? I don't get into that. I have scenarios and I have securities. Are they consistent with each other? I'm not concerned with that. That's not the theory I'm going to develop will be independent of those considerations. This is very important. I don't distinguish between options and stocks or bonds. They are securities. They have some value tomorrow and some cost today. That's all I need. How many I have? S0 to Sn, n plus 1. My cost vector, n plus 1. My payoff matrix, n plus 1 columns, and as many rows as scenarios I have. That's the setup that we're doing. And that will work if we have all stocks. It also works if I have no bond. If I have stocks and options mixed together, you name it, doesn't matter. My setup is very general. And it's so general because by that generality, as you will see, one of the things that I could do, you could say, well, all of my securities are bonds, coupon bearing bonds. And my payoffs are the zero coupon bonds. You can think, is a zero coupon bond an option? It doesn't matter. I don't care. It's just a different payoff. And if I do that, then that's your assignment number 1. See, this slight lie in what I told you. Slight lie. Okay, slight. In this theory, we're going to take one period. There's only 2 values for time, today and tomorrow. In your assignment number 1, we have more. So in fact, your assignment number 1 and this are part of the same theory if I allow my theory to be multi-period, not single period. And I'm not doing that today. The mathematical derivation is the same. Just many more variables, many more sub-indices, and much more I'm not interested. I'm not interested. Only then, your assignment number 1 and the 33 game are consequences of the same theory. If anyone is interested, I can recommend a wonderful book. In fact, it's in the bibliography of the course. You can read it on your own. I'm not going to talk about that. Not worth it. Not worth it. Okay? I need you to understand this well, and then you're strong. You can learn the rest on your own if you have to. I don't think you do. But if any one of you has to do that, some of you are doing their PhD on that, go and read it. You will understand it. I can guarantee you will understand it. It'll take you many, many hours because it's a very big theory with a lot of sub-indices. But you can walk through that on your own. We're not doing that here. Clear? Yes? Okay, so there's a few rules in this game we're doing here. There's a few rules. Absence of arbitrage, single period, I write the matrix like this. All of that is so that I can get to my objective very quickly. I have many more things that I want to talk about, and next week I need to talk about something different. That's why. Yes? Okay, I'm happy that there are many, many questions you can ask yourselves, and what about this, and what about that? And all those are great questions. Very likely they've been answered, and there is some of the books in the bibliography. All right? And if someone says, well, damn, I wish I would spend another week talking about, not this course. Sorry, at that point, I have more important things to talk about. Okay? Not to say that they're not important, and I can see from your questions you have curiosity about other things. This is good. It's just not this course. This course is a 12-week course, and there's no 13 weeks to it. All right? Okay, so everything can be priced. So the general method for pricing and replicating, that's what I introduced earlier. I have if I'm given a payoff of a certain type, then I can find the replicating portfolio by essentially solving this equation. And here, I don't know your name, but you asked me a question about the matrix. This is the reason why my payoff matrix is not only a way to organize information, it actually has algebraic meaning. And it's expressed right here, because any portfolio given by components V1, Vn will have a payoff which is that algebraic product of the vector times the matrix. Okay? And if that's the case, then everything is now an algebraic equation. Everything is going to be very, very simple, because the replicating portfolio is give me your payoff, and I multiply on the right by the inverse of the payoff matrix. So I need my payoff matrix to be invertible. That's why I need the span to be all of our n. And everything you learned in linear algebra now makes sense. All right? That's a consequence of the fact that we chose the right way to organize information. Some books organize scenarios and securities differently. Take the transpose, and that's the formula in the other book. Right? And the derivative will be the value, the cost of the replicating portfolio, which is the dot product. So here I have two dots. The dot to the left is a matrix product. The dot to the right, actually no, sorry, I wrote it correctly. I took the transpose of the cost vector, so every dot represents matrix multiplication, not dot product. As you know, the dot product is the matricial product times the transpose, right? So that's what I have there. So the price of my payoff security is the value of the result of that matrix multiplication. I have a vector transpose on the right, I have another vector on the left, a matrix in the middle, the answer is a number. And if I was you, I would not even try to understand what all that means. I would just say, of course, everything, to just follow your nose. The vector, the replicating portfolio, is the vector that comes from the solution of that equation, which you obtain by multiplying by the inverse. And once you have a portfolio, what's the price of a portfolio? The dot product of the portfolio times the cost vector. But the dot product is multiplication by the transpose of the cost vector. And that's what I'm doing here. So if I write for the P there, my payoff matrix for the 33 cent game, 1, 1, 2.5, and I write for the payoff on the left, 1-0 for my option, 1-0. I give you $1 if the stock goes up, nothing if it goes down, 1-0. And then I write the cost vector on the right as 1-1 because the stock and the bond were both priced at 1. And you solve that, the answer is 33 cents. So this is the number 33 cents written in yet a new expression again. By now we've seen how many ways in pricing that game, 33 cents? How many? 5? I don't know how many. We're going to see a few more. Yes? And they're all relevant. Because in different situations, you have to use different techniques. Sometimes because of speed, sometimes because of simplicity, sometimes because of other reasons. Okay? This is the matrix expression of the 33 cent price. That works with a million securities and a million scenarios. This is a peak we just got here. There are a couple more peaks, but are we good here? Yes? I cannot lose anybody. This is not hard anymore. You may be running out of oxygen because of the altitude, but it's okay. Are you good? Everybody's okay? Look at me and say yes.
Yes.
Now, have a reflection, and this is, again, a philosophical reflection. I'm going to spend 5 more minutes on this equation which is solved, not because I want to beat it to death, but I want to find a new meaning in that algebraic expression we just developed. So this is the worked out expression for the product of the, if I look at the P inverse times the cost, that's a certain vector, a row vector. So you were trying to multiply the matrix? Well, that's another. But here what I'm doing is, look what I'm doing. Look what I'm doing. I'm trying to find the price of V as V times something. So I'm trying to see what I multiply V by, so it always gives me the price, right? That's what I'm doing. Well, what I have to multiply it is by the inverse of P times the cost vector. Or in his language, if he likes to do infinite dimensional things, that would be the vector whose payoff is equal to the cost. Great. So in that case, what I'm doing here is introducing a new vector. I call it P1, P2, Pn. There's a reason I call them P. And the reason is that I can write the price of my payoff vector, or option, by as a combination of sums of V times P. So you could think that it looks like P represents probabilities, doesn't it? If the sum of these P's was 1, that would be the expectation of the payoff, right? In fact, in the 33 cent game, the result of this was 1/3, 2/3. It was actually what we call the risk neutral measure. It was actually a probability. Then we could say that in this new probability space we just found, and you can count the actual, this is actually assignments of probabilities to the actual events. So then from this expression we'll recover the risk neutral measure. But wait, because the problem is that P1 plus P2 plus blah, 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 plus Pn, does it equal 1, yes or no? Does it equal 1, yes or no? If it equals 1, there will be a probability. We can think of this as a probability, yes? But does it equal 1? It depends on interest rates, because if we apply this to the bond, the price of the bond today is the sum of those P's. How interesting. You see what I'm doing? I'm applying the formula that we had to the simplest, to the trivial security. And then what I realize is that the sum of those p's is equal to the price of the bond. So if rates are 0, it is a probability. But if rates are not 0, if b is less than 1, then it is not a probability. I need you to understand this. Now this is, suddenly the course has turned into a course in English. Yes. Yes.
Okay, wait. So can you then just divide everything by? Can you just divide out?
That's what I'm going to do.
Okay, sorry.
That's what I'm going to do. Yes, that's what I'm going to do. Okay? Gave a spoiler. But this is good. It's fine. You're thinking ahead. This is good. Right? So, but let's stay in this moment for one more second. If interest rates are 0, this expression we just came up with is actually a probability. And we love probabilities. They are very cute. And they're very intuitive, right? What a pity that they're not probability. But what are we going to do? As you said, we just divide by the price of the bond. We divide by interest rates. And that is, we don't have to divide by anything because the formula is there, but now it's a way of thinking. So that expression we have there is almost an expected payoff. We have to divide by the price of the bond, but that's what we call discounting. That's your assignment number 1 again. That's what we call that expression, expected discounted payoff. You understand? It may seem that this is just vocabulary. Who cares if we call it expected discounted payoff or the product of these 3 vectors? Who cares? No, you care. You need to understand. It's all about understanding. You understand what I'm saying? Everybody sees that that is mathematically justified to be called expected discounted payoff. You see that? It's almost, if rates are 0, it's expected. If rates are not 0, it's discounted too. Yes? That's going to be important later, like in a week or 2. Because these are the things that we're learning. Yes? Okay. I think we are ready for the fundamental theorem of asset pricing now. This is episode 8 in the saga. Huh? So we're going to take a 10-minute break. 10 minutes? Yes, you can recover. And then we climb. We have 2 more hills to cover, to climb. 2 or 3, depends. This is the next one. 10 minutes. Now it's time to prove a theorem. I think we're ready for it. It's the theorem that basically says that there is a unique price. I will try to do it quickly. I'm not going to spend a lot of time on this, but I do want you to see how a lot of the things can be formalized into a theory. So to recap one more time, we're going to be given a set of securities, bonds, options, we don't care, securities. They're going to have known costs and random payoffs. And a portfolio will be defined as a vector in Euclidean space that represents the number of securities in each of the securities that exist that are given to us. We're going to require that the absolute number, in the case of infinite limited securities, and I'm looking at you, we're going to assume that that this portfolio, this vector is in L1. It's finite. The payoff of each security will be a random variable. And now I'm going to write the random variable slightly differently to recognize the fact that they have a random nature. So they're not going to be given by a vector, they're going to be given by a random variable. But of course, in the case of finite probability spaces, that random variable is a vector. So, And we're going to assume that there exists a measure space with all the possible outcomes. I'm going to assume that they're finite, but if you want to assume they're infinite, this theory will work there too. So in the case of infinitely many, you're going to have here by payoff matrix, it's a matrix, the way I organize my finite information. But if I was dealing with infinite information, which is what you're thinking of, then that's what I would do. And I would have random variables, but infinitely many of them. So how do you do that? Well, that's how you represent your Hilbert space. I'm going to require that everything is a Hilbert space for the infinite theory to actually work. So the payoff is going to be a random variable that is going to have, it's going to be an L2. If we only care about finite situations, then everything is finite. You don't have to worry about this. But for people like him who want to think of the infinite, this is a requirement. I need these payoffs to be square integrable or be part of L2. By doing this, it's not that I'm killing two birds with a stone. I'm not killing anything. I'm just giving you, for those of you who are interested, I'm giving you a preview of how the general theory looks like with infinitely many everything. I'm not going to give you a preview of the same theory, which is dynamic. That I'm not doing. That requires even a bigger formalism. But this formalism is very easy to develop. It comes for free. So I'm going to choose it like that. And markets will be complete when the span of my vectors, that could be infinite, is all of the possible square integrable functions. For us, in the case of the finite probability space, that is the Euclidean space. So it's exactly the same definition we've seen before, twice already, just expressed differently with heavier mathematical formalism. And we just want to reflect on the fact that given a payoff, the price is a linear function of P. Now, what does that mean? In the case of finitely many scenarios and securities, the price of the sum of two payoffs is the sum of the payoffs. So that's to say it's a linear function. In the case of infinitely many securities and infinitely many dimensions, then linearity is not enough. You need also continuity. In the case of finitely many securities, we don't need continuity. Everything is continuous always. Matrix is always continuous. All right. So in this context, we're going to introduce a new object. It's going to be a close relative of many of these other family members we've developed in 2 weeks. But the new element is a state price deflator. It's going to be a random variable or a vector that helps us discount future payoffs, in the sense that the price of any portfolio, the price of any payoff, will be given by the expectation of the payoff of the portfolio. That's D dot theta. I remind you, theta is the portfolio, D is the payoff. I wrote them D now, and pi is a random variable. So the expectation of this product, sorry, a random vector. The expectation of this product will be the price of the portfolio. I'm not doing anything new. I'm just using some new notation again. Okay? I'm using new notation because I'm going to create new objects. What this does is think of this as, I will give you an example in the end that will clearly show this, but think of this as the following. When we played the 33-cent game and I told you the probability was a half if the stock goes up and a half if the stock goes down, someone was tempted to price that as a half. Then we said the actual price is a third, right? So without the state price deflator, the expectation of the payoff would have been a half. So that state price deflator, what it's going to do is you're going to change the wrong answer to the right answer. You see? Okay, so I'm trying to link the variables on the screen to our experience in the last day and a half. In my 33-cent game, the portfolio would have a payoff which is 1-0. The 1-0 payoff would give me an expected value of a half, but we saw that it's not a half. So another way of approaching now the pricing is going to be, I'm going to multiply by a random variable that will fix things. Think of pi as the fixer. It's going to take our wrong approach and make it right. Yes, sir.
What's the measure measure on the expectation measure?
Okay, the measure and the expectation is whichever measure you're given. So all of this is, when I said there's a probability space, right, that comes with a measure. So typically the measure is the wrong measure, a half-half, right? And I say, well, I don't care. Even with the wrong measure, I'll get the right price by taking the expected discounted payoff. But pi, this state price deflator, is the one that will fix things for me. So it could be any measure. Different measures will give a different pies. A preview of what's coming. This pi is going to be the radon-nicodym derivative of the measure given to you and the risk-neutral measure. But that's coming later. Okay, you're not supposed to know yet. Okay, so I take a portfolio, which is a vector. I multiply it by the payoff. So what I have there is the payoff of the vector. We've gone through that matrix multiplication in the last half hour. And then I modify by this random variable that will take whichever measure is given to us to be like the risk-neutral measure. So the price will be the right one. That's what these that's the approach we are taking. I remind you, there's the efficient market hypothesis that says that there are no arbitrage opportunities and there are no transaction costs. The real world isn't like that, but our world today is like that, and that's how we will understand the real world once we're done with all of this. So in this context, the fundamental theorem of asset pricing basically says that efficient markets have a state price deflator. And there are no arbitrage opportunities if and only if that random variable is positive. So if you have the random variable, the components of it will indicate if there is an arbitrage opportunity or not. That's the flagging system I told you we're going to come up as a bonus from having this theorem. If markets are complete, the state price deflator will be unique. That's what the fundamental theorem of asset pricing says. Okay? Again, it's the same thing we've been saying for now almost 2 weeks, but now expressed in a very clear, formal sense of the term. So I'm going to prove it, and I want to prove it very quickly. I don't want to linger too much on that. I want you to see how a theorem like this is proved, and that's it. I have more important things to do, and that's what I will do. So I want to prove in 2 steps. First, I will prove that if pi exists and is positive, then there are no arbitrage opportunities. And then I will prove the reverse. Then I will prove that pi must exist. So step 1 is assume there is an arbitrage. I am assuming that pi exists. So now I'm saying assume there's an arbitrage opportunity that is a portfolio with a non-negative payoff and a non-positive price. If that exists, well, I have a direct contradiction because the price of my portfolio has to be the product of all those 3 variables, the portfolio payoff and the random variable. If the payoff is positive and the random variable is positive, this is impossible, with the added remark that I need to have a positive probability that my payoff is positive. Okay? So this is a contradiction. You've seen this. It's a well-known theorem in calculus that if you integrate a positive function, the result has to be positive. If the function is positive and is strictly positive in a set of non-measure 0, so measure greater than 0, then the integral has to be positive. You've seen that, I assume. That's what this is. So if the state price deflator exists and is positive, there can be no arbitrage opportunities. Essentially, they make the expectation of a positive random variable negative. Now, let's go to the substantial part of the theorem of the proof, which is the fact that if there are no arbitrage opportunities, how do I know that such a measure exists? And for that, I'm going to do a linear algebra or functional analysis argument. I'm going to consider the space of all possible payoffs. It's a Hilbert space. In our case, it's a Euclidean space. In the case of infinitely many variables, it's a Hilbert space. In our case, it's a finite space, so it's a Euclidean space. And we're going to augment it with all of a possible a price payoff combination, whether they come from portfolios or not. So this is a vector space that contains all the possible payoffs, I call it L, and all possible payoffs not from those portfolios, okay? And I call it R. So it's the augmented vector space. And in this augmented vector space, I consider the hyperplane, which does come from portfolios. Again, the vector V does not come from portfolios. The hyperplane does come from portfolios. And on the first component, it contains the negative of the cost. And on the second component, contains the payoff of all possible portfolios. So the second component is in my space of payoffs, so it's in my vector space L, and the first one contains all the negative costs, which is part of the real line. So this augmented vector space contains this hyperplane as part of that. It's the hyperplane, which is the financial hyperplane, is the one that comes from portfolios. Everything else in that vector space is not financial, does not come from portfolios. That's what that is. And obviously, yes, Q is the cost vector. And on that, I consider the cone that contains all the positive real line cross product with all the positive payoffs of all portfolios. That's a cone. You know what a cone is? In a vector space, a cone is something that if you multiply it by a scalar which is positive, it still is in the set. That's what a cone is. So absence of arbitrage implies that the intersection between the cone and the hyperplane is the origin, nothing else. Why? If there is something which is in the cone and in the hyperplane, it is going to be an arbitrage opportunity. It's going to be a portfolio that has a negative payoff and a non-positive, has a positive payoff and a negative price. Cannot be. So absence of arbitrage has a very interesting geometric interpretation, which is it says that I have a cone and a hyperplane and they only meet at the origin. Everybody sees that? Geometry. Algebraic geometry. Yes? Okay, I don't want to linger too much on that, but that will be the picture of what I have. That's my hyperplane. It's a hyperplane, which is financial. All the portfolios on the payoff variable and their negative cost on the real variable. And that will be my cone. The cone of all the non-negative payoffs and non-positive prices. And absence of arbitrage means that they only meet at the origin. So if they only meet at the origin, there's a very interesting mathematical result that you have seen in linear algebra. You may have forgotten, but you did see it. Everybody teaches this, which is it says that I can map this vector space into the real line in such a way that the in such a way that the hyperplane goes to 0 and the cone goes to the positive real line. I can always do that. A way to think about that intuitively in geometry, this is in finite dimensions. In infinite dimensions, you need the Ham-Banach theorem. Those of you who know what I'm talking about. If not, it's okay. This is actually the projection on the orthogonal to the hyperplane. That's the linear function we're looking for. So the projection on the orthogonal to the hyperplane will send the hyperplane to 0 and will send our cone to the positive real line. It's a linear, continuous map. If it's a linear continuous map, it's given by what? By a matrix, right? So if it's given by a matrix, what I can do, and this now is where the functional, the infinite dimensions and the finite dimensions, they actually, they give us the same formalism, but the path to get it is completely different. But it's called the separating hyperplane theorem. So there exists a function that will map the vector space into the real line with the property that the hyperplane goes to 0 and the cone goes to the positive real line. They're projecting onto the orthogonal to the hyperplane. So the hyperplane goes to 0 and the cone, which only means the hyperplane at 0, goes to the positive real line. And this linear map can be has to be written by a multiplication against the matrix, because I have a vector and a Euclidean space that will be a dot product against a number and a fixed vector. I call them alpha for the number on the price side and phi for the number on the payoff side. And my functional will send, is written like this. That's the dot product on the right-hand side. And this will send my m to 0, which means that the fact that it sends the hyperplane to 0 means that the negative price of of each portfolio plus the expectation multiplied by that vector is equal to 0. I've lost you. I don't care. I really don't care. I just wanted to show you this. If someone cares, you can walk through this. I have no interest that you, this is not that, this is the one time when I really, for the rest of the course I want you to be with me. Now it's okay. I'll take a poll at the end, see how many people understood. And then if the number is close to a third, I'll be happy. Okay? This is not that important, but I want you to see it. So the fact that it says the hyperplane to 0 means that the price of every portfolio is the expectation of exactly what you have there, because that combination of price expectation has to be equal to 0. And I'm done. That's the state price deflator. It exists and is unique. And if there are no arbitrage opportunities, it's going to be positive. That's all the time I wanted to spend on the proof of this. If someone expected something, I'm disappointed, I don't care. Sorry, I don't care. So let me take a poll. Who understood this? Less people than I thought. I was hoping for 10 people or so. Okay. Anybody's interested that I explain it better? You are interested that I explain it better? Yes, you are? Okay. Then I will explain it better. I have no particular desire that you understand it. Okay? I have a desire that you see it. Understanding this, I don't think is important. Not in this particular course. So, let me see. Did I have everybody at this picture? I defined some weird vector spaces. Yes? Okay, so there was a hyperplane. It was a vector space that contained all possible prices, real line, and then all possible payoffs, payoff space. And then on that, I define a hyperplane, which they come from portfolios. So for every portfolio, the portfolio has a payoff and a negative cost, right? So think of the cost as being on there, and here to be the payoffs. High dimensional space, maybe infinite dimensional space, and then a real line going on top of that. It's a cross product. Yes? And then I consider the cone, which is all the positive first variables and all the positive payoffs. They can only meet the because the hyperplane contains the negative cost and the cone contains the positive first variable, so they cannot have anything in common because that would be an arbitrage opportunity. You understood that? Yes. So now I have geometry, a cone and a hyperplane, and they only meet at the origin. So there is a function that maps the whole space into the real line, sending the hyperplane to 0 and the cone to the positive real line. It's called the separating hyperplane theorem. But you think of it as the projection onto the orthogonal to the hyperplane. It has to send the cone to the positive real line, and of course, it sends the hyperplane to 0. There is a function. Well, a function, if in infinite dimensions, I have to invoke the Ham-Banach theorem, and this is very complicated, and I'm not going to do that. But in the case of finite dimensions, which is what I'm concerned with, this is a multiplication by a matrix. And because I have, that's what, so if m goes to 0, the cone goes to the positive real line, right? Good. So this has to be given by a multiplication by this is the function. It has to be, this is the characteristics of the functional again. It sends the hyperplane to 0 and the cone to the positive real line. We got it. But it has to be given, and this is the important part, it has to be given by a multiplication by a matrix. In the R, a matrix is a number. I call it alpha. In the payoff, because it sends the payoff space to the real line, it has to be multiplication by a very large fixed vector. I call it phi. The dimension of phi is the dimension of my scenarios. How many scenarios I have? If I have 1,000,000 scenarios, phi will have dimension 1,000,000. Phi lives in the same space as the payoffs. It has as many components as scenarios I have in my sample, in my database. Okay? Okay? This is algebra. Such a vector must exist. Call it phi. And such a number alpha must exist. I call it alpha. This is algebra. It's the separating hyperplane theorem. My functional is written like that. Where the dot product, what's the dot product? In probability space, the dot product is the expectation of the product. Okay? And because it sends the hyperplane to 0, that means that for every portfolio, the function sends that portfolio to 0. In other words, this expression is true. The negative of the cost is equal to the expectation times that vector phi I found. If you're mystified by the expectation, take the sum of the products. Is the dot product, right? That's what a matrix multiplication is against the vector. I'm writing the dot product as an expectation if you want to know where that's coming from. And now I'm done. Because I send that negative thing to the other side and I have that the price is equal to the expectation. I'll do some cleanup. I have to divide by alpha, but I'm done. I don't know phi. There exists a vector because every linear map is multiplication by a vector. You saw that in linear algebra also. I don't know rest. You can find it. You can find algorithms that will give you that vector. Therefore, this pi, this state price deflector, is algorithmic. You can actually find it in finite dimensions. In infinite dimensions, it is actually not algorithmic. You cannot find it in infinite dimensions. You cannot. In general. Okay, in Hilbert spaces maybe, but in general no. But it's algorithm, and there you have it. Yes.
So the pi is the state price deflator, right?
What?
The pi, like the pi that we get at the very end, that equals or the pi that equals phi over alpha, right? That's the
Right.
state price deflator, right?
That's right.
And so basically, what this is telling us is that like we can always find one of those values and like adjust.
There's
the
always.
price.
Yeah, so this tells us, again, this is a theoretical result. It tells us there is always a state price deflator, which implies prices are unique, and there are no arbitrage opportunities if pi is positive. That's what it means. And it's the proof of that. In finite dimensions, there are actually easier ways to calculate this pi than go through the theorem. I'm gonna show you. I have an example where it'll become clear that this is just another way of looking at exactly the same thing we did last week. Perhaps the most sophisticated way of doing what we did last week. Okay? I am not, I wanted you to see it. This is not something that I need you to understand. I'm happy that you saw it. That's it. So who understood it after this recap? Who understood it? Oh, that's good. I'm very happy. Who did not understand it? Who wants to understand it? You still want to understand it? Okay. All right. I really don't want to spend too much time on this. It's I wanted you saw it, right? You walk through that and say, oh, okay, with enough time you could probably, if I give you half an hour, you could actually get it yourself. Yes? Maybe I do a video and I explain it to you in a video. That's it. Actually, I have a video about this. Maybe I'll share with you. Yes? I really want to move on. Okay, this is not something I want to linger on. Everything else I told you today and last week is very, very important. This theorem is important and the proof is important, just not so much. Allow me to go on? I don't like usually to go on when people don't understand, but in this case I'm telling you it's not it. Okay, so let me go to the example. The example is more important. If you understand the example, I'll be happy. Okay, and the example is something I would like everybody to understand. So let me go back to the 33-cent game. I remind you, 0% interest rates. I had a stock that has a 50% chance of going up, 50% chance of going down. That was important. It was part of my statement of the theorem. I'm given a probability space. Could be the wrong one, but I'm given a probability space. That's important. So I have my cost vector, my payoff matrix, and a probability space which is wrong in quotes. Okay? Then, because the state price deflator exists, the state price deflator in this case is going to be a random variable, which therefore means I have two scenarios, right? Stock goes up, stock goes down, a very simple probability space with only two events. So in that case, my random variable is two numbers, x, y, or pi 1, pi 2. Okay? Pi 1, pi 2. So on the bond, the price of the bond is 1. That means that the bond has a payoff which is 1, 1. The probability of the bond of the bond going up to 1 is a half. The probability of the bond going down to 1 is half. The probability of the first scenario is a half, second is a half. Probability that the bond goes up to $1 is a half. Probability it goes down to $1 is a half. I know it sounds silly because the bond doesn't go up or down, it's $1, but that's the notation we're using, right? That's what the payoff 1, 1 means for the bond. The bond is always going to be 1. There's a half probability is 1 and it's a half probability is 1 because these are the scenarios that I'm considering. And for the stock, I have a half probability that it goes to 2 and a half probability that it goes to a half. So that's what the state price deflator will have to satisfy. That's what the theorem says in the 33-cent game. Okay? And of course, there is a pi that exists and is unique. Is that one? This is a new object. We've never come across this thing before. We've never seen a 2/3 and a 4/3 combination yet. So yes, it is a new object. And it's, you see, the 2 and the 4 are there to kill the 1/2, because the 1/2 is, we know, is the wrong probability. That's what it does. So here you can see very clearly that the objective of this pi is twofold. Is get rid of the wrong probability, give me the right one, and then do the expected discounted payoff. So there are two things built into the state price deflator. That's what's important. It does two things for us at the same time. It prices the bond, and now we know that it prices everything. You can price the bond, you can price the stock option too. The price of the stock option is 1 and 0, right? So it'll have to be pi of 1, which is 2/3, times a half, which is the probability it goes up, and the payoff, which is 1. The answer is 1/3. There you go. This I want you to understand. It's a very weird way of writing what we did a week ago, yes? But it's consistent with the setup of the fundamental theorem of asset pricing, which is the fundamental of the capital asset pricing model. Yes?
What does pi 1 and pi 2 represent?
Say that again?
What does pi 1 and pi 2 represent? Like it's supposed to be the state
Oh,
price deflation.
okay. I don't know what they represent. Let me put it like that. I don't know what they represent. I just proved to you a theorem that I brought out of a hat. And the theorem says, given any probability given to you, which might be wrong, take the payoff of your security, multiply it by this magical random variable called pi. Multiply it by it. And then take expectation, you'll get the right number. So what does it represent? I don't know. It's a fixture. It's a random variable that I, given any probability distribution driving prices will price everything correctly, taking expectations. That's what it does. I don't want you to think of it in any other way, as rather than to say it is the probability that prices everything right. I'm going to tell you what it is in the next slide. I'll partly answer your question, but I don't know what it represents. It's just a way to get the right price for now, okay? Yeah, you.
So I thought we initially said that the probability that the stock goes up or down doesn't matter for pricing it.
Correct.
But then here, we're kind of using the probabilities as an
Yes, but that's why pi is there. Pi is there to fix it.
Okay.
Pi is there to fix it. You change the probability, pi will change.
And then it will still give you the same price.
Always the same price.
Okay.
Yes. So it is true the price is independent of the probability. But I just wrote to you the price as the expectation of something, therefore using the probability, but there is pi to fix it. The state price deflator will fix whichever choice of probability you have. Now, we can think of this as follows, and this slide, again, I don't need everybody to understand, okay? So if I define the expectation with a weight, what this does is it helps me get the expected payoff to be the price using the right weight, as you have here. This is for those of you who know integrals with weights. You may have seen that. Some people call it the Stieltjes integral. Okay. And for those of you who know, the state price deflator is the random-Nikodym derivative of the measure, real-world measure, with respect to the risk-neutral measure that we defined last week. And I know that many of you do not know what the random-Nikodym derivative is. I know that. So I don't need you to understand this. But for those of you who know, this is perhaps my way of closing the loop. And if I'm right, I have nothing else, and we're never going to come back to this anymore. But I need you to know everything else except the theorem. I just need you to know that there is a theorem, but that's it. Yes? It's are we good? Are we good? My last episode is episode 9. It's talking about exotic options, and that's going to be a lot of fun, something that I know I'm not going to be able to finish today. I'll have to start with this next week, but it's very, very cool. Very, very cool. That's what I want to do next, but I want to know if you've recovered from the theorem. You've all recovered from the theorem? Yes? It's not my style that someone doesn't understand something. It's very rare that I do that. But this is one case in which I just want you to see it, and then I don't really need you to understand the rest of it. Am I allowed to continue? You need some time to recover? You need another break, or shall I continue? I'm here for you. Just tell me, I don't care. Continue? Okay, continue. All right, so what I'm going to do now is we've climbed a pretty tall mountain, okay? Pretty tall mountain. In fact, some of us went up to the peak of the fundamental theorem of offset pricing, but now we came back down to be with the rest of you, okay? And now, what I want to do is, even from this peak, without the fundamental theorem of offset pricing, there's a very nice landscape ahead of us. And this objective I'm going to do now is just to show you what we can see from here. To show you what we can see from here. And for that, what I'm going to do is I'm going to tell you about exotic options. First, I'm going to start telling you about American options first. Something which you probably already know and is quite simple. What I have here is a diagram that is the price of a European option with the stock tree on the left and a strike price of 75 cents on the right. Right? So I walked you through this just in case you forgot. We did this last week. We haven't done this today. Last week what we saw, so look here. When when we are at expiration, okay? I remind you that's how we do dynamic asset pricing theory. We start at the end and we go back, okay? So at expiration, if the stock is $2, my option is 125 because the strike price is 75, right? And if the stock is $1, my option is 25 cents because the strike is 75. And if the stock is 50 cents, it's nothing. It's worth nothing because the price is lower than the strike, right? Remember this? Okay, good. And then I remind you what we did is we walk backwards. So in other words, what we do is we focus on each branch. We take each branch at a time. And then we just deal with each branch. And what I have here for you is have the replicating portfolio. The underlying is 1 unit and the bond is minus 75 cents. That replicates the option, and then we can do that, we can do that. And once we're done with that, then we go and do this one. And I remind you, at doing this, there was a very important point, which was that we took the option payoff as the option value, because we don't distinguish between something given to us in cash or as a security. We don't distinguish. Absence of arbitrage. That's what we did last week. So remember that? Okay, good. So with that, what I'm going to then do, oh sorry, I went the wrong way. What I'm going to then do is I'm going to focus on the payoff now. For a European call, the payoff is at maturity. You have to wait 2 days. But that's what the term European means. Has nothing to do with Europe or the European Union or the Euro or Germany or France. Nothing to do with that. Okay, there's some old story as to why. Not important. But now here's the question: what if we could exercise early? When you're impatient, the stock goes up to $1.50, and says you're there. I said, damn, if I could only exercise now, I will make 75 cents. Right? But I said, no, sir, you have to wait. You have to wait until tomorrow. I said, but tomorrow, I mean, yes, sure, I can make $1.25, but maybe I only make 25. I really want to get out. That's an American option. You don't have to wait. I'm not saying that Americans are impatient or anything. There's no political statement here. They're just called like that, all right? In a few weeks, we'll talk about Asian options. There is something related to the history of Asia, but I'll tell you that when we come there. Not here. So the key here is to price the American option. The key is to price the European option first, and to understand the pricing of that very well. Okay. So imagine you're there. Imagine you're there, and the stock is at $1.50. Imagine you have an option. You can exercise for for 75 cents, so you can pocket a profit of 75 cents, right? Then, can I have someone trade with me? Anybody wants to trade with me? Trade with me. Good. Okay, so let's go. So you're there in that situation. The stock is $1.50, and you have an option. You could exercise and get 75 cents now, or wait. What do? Exercise or wait? You wait. Okay. Why would you wait? Okay, we don't know. But what drove your decision to wait? Don't have to answer. It's a rhetorical. That's why I need. If we follow the arbitrage-free thinking, which we've developed here, I said, exercise, not exercise. Wait, or take my money now. The decision should be purely financial, right? So what we need to understand is the value of exercising, we know 75 cents, and the value of waiting. What's the value of waiting? The value of waiting is an option, right? So what's the value of the option? If you wait, 75 cents. The value of you understand what I'm saying? There's 2.75 cents going around, and I don't want you to be confused. They come from different places. 1.75 cent comes if I exercise. The stock is $1.50, the strike price is 75. I have the choice of saying, here's the option, give me the 75 cents, and I'll go home. I don't wait for tomorrow. That's 75 cents. That's $1.50 minus 75. Or you say, I wait. The minute you say, I wait, you're European. And then, so what's the price of that? Well, you calculate the price with everything we've seen in the last 2 weeks, is the price is 75. That's what we do, right? So let's address now this. That's how we're going to make decisions, right? Purely rational. Not, oh, I'm in a rush, I need the money now, I have to pay for my tuition. No. Purely rational. And the question is, Shakespeare gave it to us, is to exercise or not to exercise. Suffer the links and arrows of outrageous fortune. Yes? So let's think about it. If we exercise, it's very easy. Because if we exercise, you don't need any finance, you don't need this course. $1.50, 75 cents, the difference is 75 cents. Grade 2, grade 1, kindergarten is all you need, right? And you go home, and that's it, you forget about this. And waiting, so well, that's where it comes from, okay? You understand? Don't exercise, waiting is, well, you have to take this course. But we know the answer. The answer to that is, we are in a European branch. Don't exercising is European. You wait. Then you have the price. And the price in this case is 75 cents, we're indifferent. That's how we're going to approach the action of exercising or not. Understand? This is very interesting. We're beginning to price actions. So far, we've priced securities. Now say, I can price securities. We're done with that. We even saw the theorem. Saw, not understand. Saw the theorem. But now I'm going to get into pricing actions, which is very interesting. Yes? Do you want to see the whole story? Okay. So the decision variable to decide if I exercise or not is very simple. Waiting is European. Exercising is cash in your pocket. You just compare the two. Waiting is European. We know how to price that. We saw it earlier. Cash in your pocket, you just count and you compare. If the cash in your pocket is higher than exercising, if the cash in your pocket is higher than waiting, you exercise. If waiting gives you more value than cash in your pocket, you don't. That's how we resolve that dichotomy. Very simple and completely rational. You all following me? Everybody? Great. So if you understand that, let me now take you to the world of swing options. I'll tell you what they are. They are very, very interesting. So swing options, they come from the energy markets. In the energy market, you have something very similar to what we did here. In fact, I used gas and electricity earlier, a couple of weeks ago, when we were talking about options, remember? The stock going up could be a stock, could be the US dollar, could be natural gas, could be electricity. Natural gas and electricity gave us some issues, which was we had to pay for storage. Remember that? We talked about that? Okay. Now, this comes in a different form now. When you're dealing with physical quantities, you can buy as many stocks as you want. But when it comes, for example, natural gas, volume matters. 1 cubic meter is okay. 1 million cubic meters is a big thing. Where do you put it? Right? So in that context, what traders realize is that in some situations the volumetric constraint introduces a limitation and a different way to price your derivatives. And it's used by consumers and producers to hedge their exposure, but unlike with dollars or bonds, which take no storage, the volumetric considerations give rise to a different way of thinking, which I will show you, okay? And the way to show you is not with gas or with oil, is with this object that you can buy online. You may have heard of this. It's called the Air Canada Flight Pass. Anybody knows about this? Air Canada Flight Pass. This is not an advertisement for Air Canada. okay? In fact, I used to go to New York several times a month for many, many years, okay, when I was running my company. And sometimes you go to New York and it's very cheap. Sometimes you go to New York. Once I flew to Chicago, I had to pay $1,800. I had to go like tomorrow. Pay, baby, pay. And that's what I did, right? So there is a way to find protection against that with this thing called the Air Canada flight passes, which I want to show you how they work because they are a swing option. And rather than use electricity or I want to use this, it's cool. Okay, so anybody had heard of the Air Canada flight passes? You have? Yes? Anybody else? Anybody was a buyer of the Air Canada flight passes? I bought them until they changed them 1 year and they said you have to go on only one type of fare. Even if there's a cheaper one, you have to go on that one. And sometimes that fare was not available. You can use them. So I said, you know what? That's the end of it. I never bought one again. This is not an advertisement against Air Canada, okay? It's just that there's a lot of fine print. But I'm going to ignore all of that and I'm going to look at this from the perspective of what Air Canada is giving you. It's very interesting. So look there. You can buy 10 flight credits. This is what's called the New York and Boston commuter. So it's only to New York and Boston. And you can buy 10 credits for $3,822. What does that mean? You
get 10 flights for that much.
That's right. So you buy 10 book of tickets and you can go 10 times to these destinations and you prepay $3,822 and then you can exercise them whenever you want and you go. Yes? Now there's another interesting consideration here, which is the average price per trip is $382. Yes? But what happens if you want to go to New York and then you can get a ticket for $200? What do you do? Does Air Canada force you to buy this? No, then it's a future. Sorry, it's an option, it's not a future transaction. It's an option, not a future transaction, if you're not obligated to use that, right? So that's the first thing. It is very much like an option. It gives you price protection. Yes? But you can't fly twice on the same flight. You could fly twice in the same day. I've been close to doing that. Okay. But you can't fly twice on the same flight. That's very interesting. Do you understand the relevance of that? The fact you have 10 tickets, is it the same to buy a book of 10 tickets as it would be to buy 10 European options on those tickets? No. If you buy 10 European options, sorry, 10 American options. American options. Okay, you decide when you fly, right? So, sorry, I'll reformulate my question. Is a flight pass the same as 10 American options on flights to New York? No, because which one is cheaper, by the way? 10 American options or a flight pass for 10 credits? Which is cheaper? The flight pass has to be cheaper because it gives you less rights. According to our thinking and the option pricing thinking we did here, if one day says, oh, I have to use this flight pass. If this was 10 American options, if you exercise one, you exercise them all. That's the way to maximize that value. The fact that you're prevented from doing that should mean that it's cheaper. Right? Great. Now, here's an interesting thing. If you look on the other side of the column, they have the small and medium-sized business flight credits. 30 flight credits for up to 10 employees. The price is $11,466. Guess what? You can fly 30 times within a year for $382 per trip. It's the same as the other number. The per trip number is the same. But in this case, you can actually exercise 10 times. because this is for companies and up to 10 people can have them. You understand this? It is not like so this is closer to not 30 American options, closer to 10 American options. And what a flight pass is really a book of options that are mutually exclusive. There's a volumetric constraint. You can't exercise more than one per time. So it's exactly the same as was developed for the natural gas market. Understand? There's similarity between the flight pass and an option on natural gas. They all come from volumetric constraints. In the case of natural gas, it's because you have the option to buy as much as you want, but not more than this. More than this, you screw my market, and then I don't want it. Flight pass is you all can fly to New York, but you can only fly once. On that flight. You can go to New York, back, and then back again. That's okay, you can do that. You understand? It's a volumetric constraint. And what I want to show you next is I want to show you how to price these contracts. It's very, very interesting. Very advanced, by the way, okay? But we are that strong. We've climbed this tall mountain, now this is like a piece of cake. Understand what I'm saying? Yes? All right, I don't know if I want to start because I won't be able to finish. And so I want to start thinking about it, and then maybe I will start with this next week when you're fully rested and we'll be on Zoom and you'll be at home or who knows where. Okay. So let me start with some considerations. Imagine I have this situation here. I have this is my stock tree, and let's say I have a payoff equal to 75 cents. And it's a two upswing. Two upswing is a call option with a limited with 2 tickets, but you cannot exercise both at the same time. Up is call, down is put. That's the language. That's an error. Cannot exercise twice. You see, sorry, I have to fix it, and that's why I hate putting this right before class. Sometimes there are mistakes. Cannot exercise twice. That's a typo. Oh no, sorry, no, it is not a typo. You can exercise twice, just not on the same day. Sorry. Yes? So it is an option. It's actually several options embedded, but they're all conflicting with each other. And what's the price? And I have to develop a terminology called P2S0, to be the price of a 2 upswing today when the value of the stock is $1. What is the price of that? Now, I'll tell you how to do the price, I think, next week, okay? But I want to ask you about this. Can you see that the price has to be between 25 cents and $1? Can you all see that? It has to be more than 25 cents, right? Because you can do is, oh great, give me the option. I exercise one immediately, and I make 25 cents, right? If you could exercise 2, you'll make 50 cents, but you can only exercise 1, 50 cents. And then tomorrow, maybe if the price drops to 75, that's it, you're done. And then it drops back to 50, you're done. So there's a possibility the lowest number you will earn is 25 cents. So the price has to be more than 25. But it cannot be more than $1. Why not? In the best possible situation, you say, well, if I wait until it's $2, is 125 times 2 is 250. No, you cannot exercise twice at expiration. You can exercise once at expiration and once the day before. And that's going to be $1, I think. Okay. But this is a more interesting upper bound. The $1 is not interesting. This is a more interesting upper bound. We know it's more than 25 cents, but I also claim it's less than 66 cents. Why? The price of the, you may have forgot that, but the price of the American option was 33 cents, was a third. So 2 American options will be worth 66 cents, 2/3. So the swing option has to be less than 2/3 of it all. You see? 2/3 is 2 American options. This swing option price has to be less than the price of 2 American options. Are you with me? Yeah? Now we would like to know what the price is. And I think that's what I would like to do to start next. Maybe I show you this and then I need your full attention and your brain to be well rested before we go through this. It's not confusing, but at first it may be. Again, now we're climbing a hill, okay? We're climbing a hill. It's not a hill which is very important. It's not something that really require you to know, but I do want you to see how, the main reason I do this is I want you to see how powerful you have become. Very few people out there, by the way, even financial professionals know how to price this. Very, very few. You can. So I'm doing this as a show of force. They say, wow, I can do this. Okay, so let me just get started, and then I'll leave it there, and then I close next week, okay? I feel I cannot leave you with the suspense of it. So we're going to follow the same approach, to exercise or not to exercise. Shakespeare has the key. If we exercise, sorry, by the way, I mean, I'm going to the problematic node. That's the problematic node. At the expression, we know what the value is, right? We know 75 cents, 25, so $1.25, 25 and 0. We know that. That's the problematic node. We understand that, we know everything. We just need to understand that node. And there, what I have is, I have a payoff. If I say, well, I save 75 cents, that's good. But once I do that, I also have what? Once I exercise, you understand what I'm saying? Once I exercise there, I collect 75 cents. And then I have what? That's the key. What do I have? I have a book of 1 ticket. A book of 1 ticket is what? It's an American option. Whose price I already know. It's in a different tree somewhere. Right? That's the key to pricing this. And if I don't exercise, well, then what? It's just a boring European branch. The price I already know. 75 cents. So it's an American option if I collect my money plus my payoff, or an American option if I don't. Or a European option if I don't. In the first case, I make $1.50. In the second case, I make 75 cents. Which one do? You exercise. We always follow that same process. We need to price our actions. We did it with American options. We're going to do it with swing options. We exercise or we don't exercise. We just value each of those decisions, and we take one. We take the one that's best for us. Okay? And in this case, we know there we will exercise, and the value of the option is $1.50. The other notes are done similarly, but I'll do the other notes next time. Yes, sir.
Oh, okay. So if you don't exercise it, then like you still only have one, right?
No, you still have 2.
But you can't exercise one.
Well, that's a different issue. We don't think like that,
Okay.
right? We don't think like that.
Okay.
You don't exercise, then you have to go by the book, which is I have my option of 2 tickets, and then I go to the next node, and then I see, and this is a European branch. See, if you don't think like me, your argument only works the day before expiration. My argument works all the time, right? If I don't touch my option is untouched. If I touch my option, if I exercise one, what I do is I collect some money, I leave that tree, and I move to another one. It's a different tree. It's the tree with 1 exercise option less left. That's the rational way of approaching it. Okay? So we're going to do this next week, because we're going to have to be very quick at pricing actions, not securities, actions. And we're going to price actions like this. What if I do? What if I don't? It's going to be like that. Every time we go to every node is, what if I do? What if I don't? If I do this, if I don't that. And we have to keep a very good database of our decisions and the numbers driving our decision. We will see that at the beginning of class next week. Preview, I will do that at the beginning. I want you to understand this, not because this is something that is, there are not many billions of dollars in these types of securities. It's just that I want you to understand how powerful you have become in your way of thinking. And then what I will do is I'll start to think what happens when I go from 2 time steps to infinitely many time steps. That requires some thinking. We'll do that next week.